Here, the role of TNCs. So we'll continue the discussion. So again, as I was talking about in the last session, TNC and the role of transportation network companies within the transportation systems has increased significantly. There was a setback because of COVID, because of social distancing, everything went down. But as you can see with new data in here for New York, it has reached back to pretty much pre-COVID levels in New York. In this, we don't have the data for 2022 2023, we're showing only up 21, but we are seeing that the rapid pickup back to pre-COVID levels. In fact, the trends are such that they'll go higher than pre-COVID levels in few years. So, TNC is here to stay and it will be an important component. So, what we are looking at here is how can we assess how TNC is serving the transportation system. So, previous research focused on what is happening because of TNCs, are what are the locations that are served by TNCs, what are the social impacts and so on. So, there were some research efforts showing that vulnerable communities are not being served, there is discrimination in terms of ethnicity, income, and so on. And also, there were some studies saying that TNCs are adding additional miles to travel because a lot of times they travel empty, and also there are other implications of that. And there is also reduction in public transit, why TNC is drawing some of its trips from traditionally public transit, especially when the weather is bad. It starts raining, people who typically travel by bus consider using TNC as an option when the weather is bad, and so those things have been reported in the. But what was lacking is what is the impact of TNC in the context of the overall transportation. What is the overall transportation demand in a particular location? How much of that is served by TNC and what governs it? So we wanted to look at that aspect. So what we did here was we focused on examining TNCs in the context of overall transportation demand. We developed a metric to identify the imbalance between overall transportation demand and TNC demand. Okay, the reason I'm talking about this specific study about TNCs is the same method can be utilized to look at how public transit or any shared mobility mode interacts with the rest of the travel. So this approach is more that way. We looked at again, it's when the metric is developed, you want to understand the relationship of the metric with the host of explanatory variables. We're trying to see whether it's the income, whether it's the employment, whether it's the population density, whether it's transportation infrastructure that is influencing this relation. So that's why a set of independent variables were considered. I'll talk about them as we go forward. And so that we can identify, the idea is to apply for any urban to identify special pockets or speed pockets where there are underserved or overserved by TNC. So again, as we go ahead, we can see this. So what we did here is we looked at the city of Chicago. All the travel data was aggregated at the census tract level. So we have TNC demand at the census tract level. We also have overall transportation demand at the census tract level. So any thoughts on how can we get the overall transportation demand for an urban region? What would we use to get that? You have to use a travel demand model, right? So maybe you can use a household travel survey based travel demand model that will give you information on the actual demand, overall transport demand across the urban region at any resolution node, right? So what we did was we got these two variables. So for every census tract, we have two information. One is what is the demand for TNC in that census tract, and what is the demand for transportation. Okay. Now both of these numbers are not directly comparable, right? Because again, this is the total demand. So total demand includes walk, bike, auto travel, commuter, all of that is included. All of that is included in the overall transportation demand. TNC demand simply looks at how many people are using Uber or Lyft in Chicago. So we do not want to come. The numbers directly are not comparable. So what we did was we ranked them in descending order, if you will, and we partitioned each tract based on a decile. What we are looking at is we have 800 census tracts. The top 10 census tracts go into decile 1. Top 8, sir. So we organize them into 10 groups in ascending order. The same thing for the overall transportation demand also. And then we looked at how do they differ. So for example, there is a census tract, it happens to be in the second decile for transportation demand. So what that means is there's a lot of demand for TNCs relative to the rest of the city in that census tract. Now then we compare it to where does it fall in the overall transportation demand. So is the overall transportation demand also very high? So then it is not underserved or overserved, right? So if my census tract falls in the third decile for TNC and falls in the third decile for overall transportation demand, it's represented. What all it tells you is we have good demand in TNC, good demand in overall transportation demand. But now if you see a zone or census tract which falls in the first decile for TNC but falls in the 8th decile for transportation, that tells you overall demand is low but TNC usage is very high in that area. So that identifies an imbalance where that census tracts are overserved by TNC. Okay? Again, just by identifying this, we are not trying to say it's bad to be overserved. We are just trying to identify a difference between overall demand profile versus overall transportation network company demand. Okay? This is just to identify the difference. So we rank them in this manner by deciles, rank 1 through 10, and then we take the difference of the ranks. Okay, that's what will give you an indication. So here we did this. So we created 5 groups. Okay, we observed the census tracts and looked at the distribution, and we used it to create these 5 groups. So if the rank of overall transportation demand minus rank of TNC demand. So what this tells you is the overall transportation demand is lower, the rank of the transportation demand is lower, rank of TNC demand is high. Okay, so this is what we labeled as TNC surplus. So this is very high TNC surplus. So we call this high TNC surplus. So balanced when there is not much difference. Again, TNC deficit, high TNC deficit. Again, the same idea. Looking at the difference of these two numbers, keep moving. So the difference is -1, that goes into TNC surplus. No difference, that tells you that both are in the same. If TNC is in the 5th decile, demand is also, transportation demand is also 5th decile, that tells you it's a balanced system. There is an expected number of TNC trips that should happen. What is happening? This is where you start seeing deficit, where you have a lot of transport demand, but there is not enough TNC serving those peaks, or TNC is underserving those peaks. Another thing is overall transportation is very high, but TNC demand is low. Now, is labeling a census tract high TNC deficit, is that bad? What would this be useful? So now I have, let's say, 800 census tracts in Chicago. As I showed in the table there, 200 are high TNC deficit zones. So that's like about 25% of the zones are in that census tracts, and so all of 25% of the city is bad. Would that be conclusion will reach? I'm asking that question, but it's not. So why should it? What are some important aspects to consider when you look at deficit? So some census tracts are expected to be deficit, in deficit. Think about suburban communities where people own cars. There is a lot of demand coming from those because they're working, they go to office, they drive and all of that, or use public transit. But because they are regular commuters, they have plans of how to get to work. So there are households with 2 cars and 3 cars, they are not going to use trains, right? So there will be some pockets with high vehicle ownership, high income neighborhoods where there is a lot of transportation demand and very little TNC demand. That is fine. Those are not problem census tracts, right? So we have to be careful. Just because we label that a high TNC deficit, that does not automatically make it a bad census tract or a census tract that has problems. We're not trying to suggest it. All we are doing here is figuring out, okay, where are the pockets where there is a deficit, And then we will further investigate. We look at, okay, what is creating this deficit? Are these census tracts people who live in communities who don't have cars, are captive riders and would benefit from TNC? That would be something we need to. So we need to study that further as we go forward. So these are the 5 categories we created. Again, there is some discussion on when we are looking at the deciles. You can actually have a score in each of the deciles, and we could directly take the difference of the deciles, right? We can take the difference of where does this fall and where does that fall, and study that also. We wanted to go with the categories. I think it's easier for this categorization. Once we create these 5 groups, rather than talking about an arbitrary score, this I think gives them a sense of, okay, oh, these are census tracts that are balanced, these are census tracts that are not on this side and on that side. So that was the idea why we created this 5 categorical weighting. So this is the distribution of the regions across Chicago. So you'll see the TNC deficit region is around outer regions. If you look at the balanced region, the gray areas are typically in the downtown region. So this is where we initially expected downtown will have actually surplus, but we did not see that. We actually see that downtown regions, the demand is actually balancing with the overall demand. What we find is high TNC surplus routes are found along large transit routes. That is where we are seeing a high surplus for TNC. So what we are seeing is people are taking TNC to get to the transit station more and then using transit. So it's actually a good thing that we're seeing. There are some locations which are in deficit. These are the peripheral regions which usually are lower income neighborhoods. And these are located, these surplus locations are located around the route. So here you have the blue lines are the metro transit route, and CDL is a metro line that exists in, so these yellow lines are here. You will see a lot of red pockets of census tracts around the metro route, the route L. So what we wanted to do was, okay, now we built the metric, we identified where each of these census tracts are. Now we wanted to understand, okay, what are the characteristics of the census tracts that drive them to one of these 5 categories. Okay? So for that, we looked at different categories of independent variables. We looked at sociodemographics, land use and built environment, transportation, infrastructure. So again, this theme, whenever you're developing a model, you would want to make sure you have a detailed set of attributes that you're considering. Usually, if you're looking at demand, you want the sociodemographic attributes because you want to see what is the employment, what are ethnicity distributions, age distributions, vehicle ownership, income indicators of any form. Okay, whatever data is available in this, that's something that is important. More and more focus is being given to land use and built environment attributes, where we are looking at, if you're looking at census tracts, you want to look at what is there in terms of in that census tract. So it could be what is the residential area, commercial area, institutional area, industrial area. All of these need to be considered. You also called a land use mix. This is a kind of entropy variable as a function of different land use types. Then we also need to look at transportation infrastructure attributes, right? So frequency of L trains, number of metro trains, and different variables. So here, DB stations are the bike share stations in Chicago. Okay, that's a company that runs bike share there. We also look at infrastructure, walking, street length, and side length of sidewalk. Again, I know some of these variables are harder to collect in the Indian setting, but whatever is available can be considered going forward. So here we were looking at how some of these variables change as a function category. So what we're looking at is percentage employed. So you see that if you have high rate of employment in that census tract, you will see that it's most likely to be balanced. Okay, so because there is movement in and out, and people use normal travel and other things. If you look at this one, if you have a large portion of non-Caucasian population in high TNC deficit zones, you'll see 40% is the share of non-Caucasian population. So what we are seeing here is TNCs are underserving minority communities in the region. But similarly, if you look at age 65, again we see that people with high see, locations with high percentage of seniors usually fall in the deficit. So basically, again, they don't have familiarity with using technology, also are not comfortable with somebody else driving, so probably they are underserved. If you look at income, again, you'll see in high income, the chance of the PMC deficit zones have very little high income. What that tells you is usually the opposite is happening. It happens in low income communities. So this is again the 5 categories that we created allows us to see these better than using a single score. If we had a single score, we won't easily be able to capture these differences across the attributes. That's why we are looking at the category. Look at vehicle ownership, you'll see that if you have high proportion of zero vehicles, it's not surprising that you will have a lot more PMC surplus. Okay? So these are locations where there's a lot of transportation demand, but people don't want to use their personal vehicle. So they are relying on either public transit or TNC. So those are census tracts where you'll have right. So you'll see that they are less likely to be in the TNC deficits without vehicles. The last one is 2 or more vehicles. Again, this is what we're talking about in the beginning. So if you have 2 or more vehicles, if you have a large proportion of 2 or more vehicles, you don't need TNC. You already own multiple cars in your household. So this happens to result in a high TNC. This is actually a desirable thing, right? If people already have infrastructure to travel, you don't need to add additional infrastructure for them. So this is not a negative thing in this context. Again, we also look at density. If you look at density, this is one of the aspects that we talked about where if you have high density of stations, they are likely to fall in the TNC surplus. Again, this is also reinforcing the fact that surplus is likely to happen when you have metro station. Same thing with the metro service here. Again, similar aspects are found even with bike. If there is good bike share systems, so this kind of reflects high activity, maybe of tourists and also discretionary activity in these locations. And then people are using a lot more TNC than in other locations. The last one is sidewalk density. Again, there are some differences, but not significant here. You'll see that with higher sidewalk density, they're more likely to the 2 categories, which is the TNC surplus. Okay. So now I'll quickly talk about the model that we developed. So again, these relationships are all nice to show, but there is no statistical significance associated with it and we don't know which of these dominates the others because it's all univariate relationship. I'm looking at relationship with A versus B, C, D, E all separately. But what is important is we want to look at when all of them act together, which of them actually means. Okay, so that's why we develop models because one-on-one relationships do not reflect any causality. They are just correlations. We're just showing correlations. We want to capture a little bit more than. So we have the 5 category variable. I'm using that as the dependent variable, and because you have 5 categories and the variable is ordered, right? We're going from very high surplus to very high deficit. There is a natural ordering of the variable, so we employ an ordered response model structure. Okay. Again, I will talk about these models in detail when we're doing the methods here. I just want to quickly show these things. So we create two so this is how the model system works. So we create 5 categories. The propensity is captured by the blue curve. That is made a function of different independent variables. So that's what I'm doing here. The YQ star, this is the propensity variable. Epsilon Q is the what gives this normal shape or logit shape for the curve. The thresholds. So usually, traditionally ordered logic models only focus on the propensity. So the curve can move to the right or the left and the probability changes. If the curve moves to the right, probability for this alternative increases, probability for this alternative reduces because that's the probability, the whole probability has to add up to 1. That is how we model an ordered response model. But in this model, what we are doing is we're also allowing for the lines to move for each individual. So depending on the particular characteristics of the census tract, the line itself can move. So we have 4 degrees of freedom. The curve can move, and 3 of the lines, there are 5 alternatives. You can only get 4 factors. So one has to be the base. So you can capture 4 differences. So you can either remove one line and three of these thresholds. Okay. Again, don't worry about the details. I'll go over that in detail because I want to start from scratch. We'll discuss that. Here, I'm just trying to show quickly. So again, this is the model structure. So we developed the model. We estimated a generalized order logic model. You can see clearly that the log likelihood is better. So closer to 0 is better. We also did a mixed logic model, mixed generalized order logic model, but it did not improve the Bayesian BIC metric. So we used the okay. So here what we are showing are the results of the model. As I said, we'll talk about the math in future sessions. Here I just want to show you some things that we're doing. Here you can see as proportion of population with age increases, the chance that they become high deficit increases. Right? We're modeling 0 is surplus, 4 is high deficit. So we're going from high surplus to high deficit. So a positive value here indicates as propensity increases, proportion of population with age greater than 65 increases, more likely to be deficit. Low income, they use. Again, if you see proportion of Latin and Hispanic population, African, so this threshold, this threshold is moving to the right, to the left, sorry, to the left. So what that means is this area will increase, right? If I move this line, the area available for the high deficit under the curve increases. So the probability of this alternative increases. If I move this to the right, the area available for the fifth alternative goes down. Okay, so that's why by moving this to the left, so that's what is happening when you have minority communities. What we're seeing here is that again, low income census tracts also the curve shift to the right. Proportion of high households, 2 or more vehicles. So here we are seeing the effect that if you have 2 or more vehicles, you are likely to be in high deficit. Okay. So you can interpret if you have high employment, you are likely to be in surplus because there is demand for TNC. We also looked at other things as you go away from CBD. So if you are closer to the central business district in Chicago, you will have more balanced structure. The further away you go, it goes towards deficit. We also identified trends that we expected for trains. So if you have L03, you see reduction in high deficit census tracts. If you have bus stops and DV stations, they can increase deficit. So what we are noticing is there is some interplay between metros and other public transit. So this was not what we found if you looked at the univariate data. But if you look at the multivariate data when we're developing this model, you will see that the bus stops are actually creating deficit locations. Okay? Because so people are using TNCs to connect to metros, but not to the bus transit system as such. Okay? These are city of Chicago has 4 spatial locations. We divided the city into 4 pieces. These are like fixed effects. We're just trying to capture factors specific to each part, central, north, west, or south, to reflect differences across TNC usage. So if just to give an example, if network's distance from CBD increases, the curve moves to the right. So what you will see is when that happens, the area of this alternative increases substantially. Okay. Now, another variable that we found for the same variable, not only does the curve move right, the threshold also moves to the left. So this even further increases the area allocated to alternatives 4 and 5. Okay, so that is the additional freedom that we get by using a generalized order. If you only use an ordered logic model, only the curve can move to the right or the left. But that does not allow for this nonlinear interaction where if only the threshold moves, that changes the probability. It gives you additional flexibility to modify the probability for the model. Okay, so that's the reason that we use this. Yeah, I'll talk about this. So we can also do an elasticity analysis because the variable impacts are not easy to predict. So if you're using linear regression, if the coefficient is 5, that tells you that if my x increases by 1, my y increases by 5. That's the interpretation of the coefficient. It's not as straightforward when you have a generalized order response model because we are tying to something non-linear. So for that reason, you need to create a computer protocol either marginal effects or elasticity effect to really understand what is happening when you change one of the variables. So that's what we're doing here. For example, here, if you look at low income tracts, if you increase low income tracts, what will happen is you'll end up with more locations in the high deficit, which again makes sense. We know this from the coefficient, but we are just showing you the magnitude of it. Same thing with proportion of households with 2 or more vehicles. If you have more households with 2 or more vehicles, the likelihood that that tract will turn into a high deficit increases. So what we did was we changed all of these 10%. All of these values were changed at the same percentage to compare and see which has more impact and which has less impact. So you see that vehicles have a large impact. Income also has a large impact. Okay, ethnicity has some impact, slightly smaller, but still reasonably. So again, here what we're doing is we're trying to come up with a metric that we can look at in the context of overall transportation demand. We developed the metric and we also explored how it relates to different independent variables. Then we developed the model, and now the model that is developed can be utilized to look at different pockets, spatial pockets in urban regions where there are problems. Okay, so we could clearly see that TNC usage is substantially influenced based on income, vehicle ownership, age, and ethnicity. Okay, so that's the main. Any questions?
Can you please repeat the slide 32 and 33?
So what we have here is, if you have a model for 5 alternatives, this is how the curve would look like. So what I'm doing here is the network distance variable has a positive impact on the propensity. So what that means is your curve shifts to the right. So when the curve doesn't shift to the right, this is a normal distribution or a logistic distribution curve. So this gives you the probability for this alternative. So if you add the area under the curve up to this point, you get probability for this category. If you want this category, you add the area up to here and subtract this. Okay, so this directly represents, so the area between these 2 lines gives you the probability for each of these alternatives. Is that clear? Okay, so we have 5 alternatives. So now, if I want the probability for this alternative, all I have to do is capture the area under this. So to do that, I'll take 1 because it's going up to infinity. So 1 minus all of this would give me the area of this. Okay, saying is when distance from CBD increases, my propensity increases, which means this will shift to the right. Okay, so now this is no longer the curve, this is the new curve. What will happen to the probability of this alternative now? What can you see? You can see that you have new area, right? So the area under the curve is now, when you compute it, it will be large. So you can clearly see that the probability for the first alternative goes down and the probability for the last alternative goes up. Clear? I can't say anything about the middle. Okay, unfortunately, because it's a non-linear system, it is not easy to say what happens to 2, 3. We need elasticity and marginal effects for that. But 1 and 5, I can clearly. Okay with that? Okay. Now, this is what would happen if you have a simple ordered logic model. In an ordered logic model, it's like tying a string to this curve and pulling it forward or backwards. Okay, that is only 1 degree of freedom. It moves left or right. Okay, or left, right. Okay. So now, in a generalized ordered logic model, I have more strings to play with. What I can do is I can pull or tug on these thresholds. So that's what I'm showing in the next slide. So this threshold, because network distance increases, the threshold keeps shifting to the left. Okay. Now what happens because of this? So we have 2 effects, right? One, we move to the right, so this area increased. Now when I move this to the left, what happens to the probability for this alternative? It should increase, right? Because now suddenly the area is not this, but this, right? So the probability for this alternative increases, and potentially this also will increase because this threshold is tied to this. It could move. Okay. So what we are showing here is 2 ways of increasing the probability. Now, if you pull the curve like this, I mess up everything. I modify everything. Right? When I pull up the curve, I change this probability, I change this probability, I change this probability, and this probability. Okay. But if I only pull on this line, I don't change anything this side. Or these two. I should say I don't change anything for these two. So what I'm saying is a variable can only affect alternatives 4 and 5. It does not affect 1 and 2. That is not possible in a simple ordered logic model. In a simple ordered logic model, if a variable changes, it affects all 5 alternatives. But in a generalized ordered logic model, by focusing on the threshold, I can create flexibility to say only 4th and 5th alternatives change, or only 3rd, 4th, and 5th alternatives change. So, the example I'm giving you here, 1 and 2 don't change. 3 changes, obviously, because the threshold is moved this way. So 4 and 5 also will change. So this is additional flexibility. Again, for people who use models, multinomial logic can do that. Multinomial logic can actually capture effect specific to any alternative. And this is used as the biggest drawback of ordered logic model. They say ordered logic models apply to all alternatives. If you do the thresholds correctly, it will do. Generalized ordered logic models are perfect equivalents to multinomial logic models for ordered variables. In fact, I work to show that if you have an ordered variable, use the generalized ordered logic model. It will perform, if not better, at least as good as MNL. And we have shown in all our examples and all our case studies, it definitely outperforms MNL. But still, there is a lot of hesitation because MNL is easily available in software, so people use that more. But we think generalized ordered logic models are superior multinomial logic models for ordered variables. Again, if you have an unordered variable, yeah, we can't use generalized order, so it doesn't work. But when you have a specific data set where your variable is ordered, please use generalized ordered logic models. They will do a better job.
We are applying logic because the variable is ordered or it doesn't follow normal, not continuous.
Yeah. So
distributed logistically. So when we apply log, actually the nonlinear function is translated linearly. That is what the purpose of logarithm is. Okay. Translate the exponential function to a linear function.
no,
So are we again and
so I'm not really for anything. Okay, the logistic distribution is simply how my error is distributed. Okay, so I am saying yq star is called the latent variable. So nobody observes yq star. We don't know what yq star is. So this is an unobserved variable. Okay, the only way I have some information is on the actual category. Okay, so yq is what we observe. It is 0, 1, 2, 3. If I take a log of that, I get log 0, log. That's not very useful, right? It's not like you have a continuous value, we're taking the log and running the model. No. Okay. We just have a discrete variable. We have 5 categories, 0, 1, 2, 4, or whatever you call it, 1 to 5, however you want to call it. And if what we are hypothesizing here is if the probability with the error term, because I don't observe it, is less than the first threshold, you stay in this category. Okay, if it is between this and this, okay, I will talk about detailed order response. I'll get it. We'll talk about it in detail because I want to start with linear regression and go. So this is just a case study, so we'll get to it. Okay. Okay. So again, I'll do the elasticities. So let's look at one thing. Okay. So this is proportion of population with age between 15 and 20. Okay. What I'm doing here is now I go into my independent variable. So I have this variable. I change this proportion by 10%. I artificially increase. So let's say it's 2% right now. I make it 2.5. If it's 5, I make it 5.5. Okay. So I create and then I happens to the probabilities and look at the change. So what I noticed is if I increase this population by 10%, these two categories do not change. This category reduces by 1.5%. Okay, this category increases by 1%. That is the interpretation. So for a 10% change in the independent variable, is the percentage change in probability for any of the alternatives. That's what I'm showing here. So for example, based on that, you can see that if you increase 2 or more vehicle households by 10%, you will reduce surplus by 9%. So that's the interpretation. So we in my group we usually do elasticity than marginal effects because in marginal effects are supposed to be for a small change. It's hard to interpret what is a small change. We don't know. So here we define the change. We say it is 10% change, and then show the elasticity. That kind of gives. It's not easy. Right? For example, I can't really change the household's ownership of two vehicles by 10% very easily, but just to reflect on, okay, if that changes, what happens? That way, we are normalizing all these elasticities for the same percentage change. So they compare, oh, this is 1%, this is 9%, so it means this variable is more important than this variable because it has a more larger change. Okay. Any other? So again, the idea of the case study was simply to show how we can create a metric, and once you create a metric, how you can analyze it and see what variables are. So we will start looking at the second module now. So with that, I finished the first module. So again, the first set of slides was on providing an introduction. Now what I want to do is I want to start looking at what is public transport data, how we can use that, and so on. So I'll talk about passenger data and also look at what do we want to analyze. How can we analyze that? That was what we'll talk about. So, different components of public transit data. Again, all of you will be aware of some of these elements anyway, so I'll talk quickly about them. So, passenger data is one of the most important. Right? So, if you want to model public transit system, you want to look at ridership, you want to look at for different origin and destination. But there are other components of data. Right? So, there is data on vehicles. So you can look at what are the fleet compositions, how many vehicles are there. The transit agencies also have to decide on some of these numbers, how many buses to own, what kind of fleet mix. I mean, are they going to have all of them diesel, how much of them electric, what capacity of those, and how are they utilized. So if you look at a vehicle, you're running a bus, and how often is it full? How often is it half? And so on and so forth. So all of these are also important data. Then you also have what are the travel information data, right? So different agencies are investing a lot of resources in providing this information readily to passengers, right? So if you have an app for the local agency and you can see where the bus is, or if you at least have some information on when the next bus is arriving at you're waiting for a bus, and if you know the bus is arriving in 3 minutes, the 3 minutes will fly much faster. If you don't know when the bus is arriving, wait exactly the same 3 minutes. Because of the uncertainty, it will feel long. Okay? So, again, agencies are recognizing value to providing information. I mean, even if it says you have to wait 15 minutes, knowing that it comes in 15 minutes makes your life so much easier. You know you can plan. So, at university, the transit system is run in a way that they actually provide when a bus is coming to an apartment. So I know students who just start walking down when the bus. Right? So it gives them that, and they don't waste their time waiting in the bus stop. They actually can do or get a plane, whatever it is. They can come down right at the time where they need to get onto the bus. So that information is easier for people, and also if there are disruptions. Right? So sometimes the bus can have a breakdown. Knowing that and not having to wait 1 hour to figure that out is very helpful. So there is a lot of work that goes into providing that, and there are also GTFS routes where geocoded routes are provided for all transit, and times are you can use that to figure out when the bus arrived at each stop along a route, for instance, and then use that to model how many times the bus is arriving on time, it's late, and so there are all of these elements that can be looked at from travel information. Then there's also the financial, right? So each time there's a ticket that is purchased, there's revenue generated, there's expenses associated with how the lines are managed, there is employees who are working, their salaries and so on. So that could be one component of financial data that can be looked at. There's also the workforce, right? So there are how many employees do you need to own? In some cases, they're outsourced to private companies. They manage the fleet, they manage some of these aspects. Again, salaries become a big component because usually public transit systems are, again, not in all cases, but usually publicly owned. So there are always challenges with respect to funding and salary negotiations, and if you have unions, there are stricter discussions that happen. So again, there is a lot of data that can be used in the realm of public transit. Okay, we won't be able to. I think years you want to cover all of these data sets and so on. So what we'll do is I will focus on the passenger data. Okay, we're talking about mainly about that, and we'll refer to other elements as necessary. But I'll focus on the detailed passenger data analysis that we can do as part of this. Yeah. So again, there are different components to passenger data. One of that is ridership. Obviously, the numbers you can look at ridership at different resolutions. Look at ridership at a stop level. So if you're a station or a bus station, how many people get on at each stop can be very that we analyze. Some people might say, okay, I'm not really interested in every stop level. All I care about is how many people are using this bus route. So that would be the route level. But there could be higher level policymakers don't really care about even each route. Right? They focus on how are the ridership number and system level, and how are they changing by different time. So again, the ridership data is very complex in the sense that not a single number. That number can be passed at different resolutions. Right? So if you think about the city bus system in any major city, right? There are the fares are also available by zones. Right? So usually they are not measured. Revenue is not measured at a stop level because there could be 6 stops from where you can get on and pay the same fare to go to your destination. Right? Because you cannot change the fare for every stop. There are multiple stops within each region where you're paying the same thing. Okay? So in that case, the agency doesn't care which stop you're getting. All it cares about is which region you're getting. Right? So sometimes they don't even collect the data at the stop level. They're not collecting how many people are getting on board at every stop. They're only collecting region. There are 5 regions for us. Region 1 to region 5 is 35 rupees. Region 2 to region 5 is 25 rupees. So they have this fare system where every region to region they have different price fixed. So all they care about is flows between these 5 regions. They might just collect that a matrix of 5 by 5. But they don't really care about which stop people are getting on because it doesn't matter monetarily. But it might be important for us to understand what happens at each stop because if you want to provide a stop station, bus station, or a location where people can stand, okay, we need to know how many people are using it because you cannot do that at every stop. You don't have the money to do it or space even to build that infrastructure at every stop. So there are challenges in how data is collected and how we want to use it as planners and engineers for improving public transport. Okay, so there are some challenges like that we need to consider. And ridership changes by time. In the morning peak, afternoon peak, evening peak. So again, that is something to look at. Weekdays versus weekends, there are a lot of differences. So again, if data is collected at different resolutions. So for example, if somebody is willing to give you data for every hour, then you can characterize that into any classification. But all they have is day of data. They are only collecting daily numbers. So they're not tabulating data on an hourly basis or in continuous time. It becomes more challenging because then you have to reflect everything. The impact of employment is varying by time, but we cannot capture. All you can do if you have only daily numbers is put that as the independent variable and focus on what is the overall employment at daily basis. So it gets tricky depending on how transit agencies collect it. Ideally, we would like to capture data at the highest resolution possible. So if you have an opportunity to collect data or request data, always start with, okay, I want it in continuous time at as fine spatial resolution. If they say we don't do that, you can always think about ways of aggregating that. But your requirement or effort should go into collecting data in as small a time scale as possible and as small a spatial resolution as possible. Okay? Because once you have that, you can do anything. You can always go from bottom to the top. You can never go. There are ways, there are approaches that can be used to go from top to the bottom, but those are all models. They are not real data. Right? So what you're getting are estimates. It's not real. So we have to be careful. Other data that is important for passengers is we need to understand the demographics and socioeconomic data. So income categories. If you're looking at any public transit system, you can define what's called a catchment area, where people from the region that are going to use that service could be a bus. So catchment areas for bus stops will be smaller, could be slightly larger for metros, and especially if you have good first mile, last mile integration. But you understand who are the users of the system. Okay, for that we need the demographic system. And the third thing that is important is we need to understand the travel pattern, because again, they govern who uses public transit or any other. So if you don't know how many people are traveling from different parts of the city to other parts of the city, we cannot design our systems to manage demand effectively. Okay, because this is what gives us that information to see, okay, now there are so many thousands of people going from A to B using car. What would it take for them to shift to public transit? How can we do that? So, but even for that, we need travel patterns. Then the last element is individual level data. So the first three dimensions are what I would call system level data, where we are capturing data from the perspective of our transit system. But individual data is where we're trying to focus on each rider. We're trying to figure out, okay, how many times does this person use public transit or other modes? What is the cost that they're paying? What purposes that they're doing? So this would be what you call a market survey kind of analysis, where you can develop, okay, how do we convert people who are currently driving to public transport, focusing on individual level. Okay, again, the analysis for the ridership data will be different than individual level data, because again, the objectives are different. But this is what defines some of the challenges in how we model and analyze. Any questions? If I am modeling stop level ridership, let's say I'm building a ridership model at the stop level, all I care about is how many people are coming on the metro or on the bus at that stop. But I'm not looking at each, because once I'm modeling the count of people, I'm not modeling each. Right? Yeah, if there are 5 people, but I cannot, there are ways how we can capture the actions of those 5 individuals is to group them as 5. It's a count. We're looking at that. But individual, I'm actually looking at what is the age, that level of detail. You cannot capture that level of detail in the range.
So in this software, kind of data combined they should be some
Yes. So what we'll look for, I'll talk about that. Well, what we look for is we use this approach. We draw a buffer in GIS, and what is the population with how much, right? As population increases, hopefully, right? So values variables you use, and also look for what is the density of transportation network in that region. Look for public transit. So all of these. So I'll give you. So we look at variables from different kinds of categories, and then sometimes data is not available to do a buffer. Then what you will do is, okay, maybe you have a census tract or some kind of larger aggregation of zones. You use that as much as possible. So I want to show some numbers here of some data trends that are happening. So I selected San Francisco because San Francisco area is an agency that provides data openly. So for now I'm just showing you. So this is ridership data So for different modes. So here are the different modes that exist in the region. So you have bus, which is predominantly the majority mode. Here you see commuter rail is the large one, heavy rail is this one, light rail is this one, and there are other modes. And ferry, ferry is very small. So what you will notice the moment you see this chart, the impact of COVID comes apparent, and you see the drop. So we were talking about bus numbers ridership has been declining. Okay, you notice that it has been declining, and then what happened after COVID? So 2021, 2020. So it has rebounded, but not anywhere close to what it was. We talked about 900,000, which is again going down, but it has not come. And it was a bright spot. Heavy rail was increasing over time. You see that in 1991 it was around 250,000. It actually crossed 400,000 in 2018, 2019, but then it dropped precipitously after COVID, and not even at. Okay, this is show more numbers. What we're seeing is COVID kind of, especially in the US, has been a big disruptor for public transit systems, and they're finding it hard to recover from that shock. People have found, hey, some of them are working from home, they found so it's a big change. So here there are different systems, subsystems within the San Francisco region. This is the bus system. So you see it's called Muni. You'll see average number of riders in billions. Again, this is the different years. We also 4 and 2025. Okay, this is 21. You'll see the drop. Biggest drop happened in 2020. After 2021, again things are improving, but nowhere close to the top. But it's getting better. Okay, so you see that it was around 0.7 billion. It's now come back to 0.5 million or 0.4 and half, 0.5 and so on. So hopefully with time things will improve. But the target they had for 2024 was 410. You can see in some months it crossed, and in some months it was close to lower than that. But usually it crossed. The target of 410,000 trips was met in 2020. So there is recovery happening, but slow recovery in this. This is another system within San Fran. You see the bus and transit. Again, this is yearly data. Okay, so over the year, ridership has been going down. We're at 13 million here. You'll see it goes down to 10 million even by 2019. But 2020 substantially from 10, it actually became half. But what is good to see is that it is recovering reasonably. So we're close to the 10 million they had in 2019, about 8.5 million. So hopefully it will recover. This is, they have Bay Area has the Bay Area Rapid Transit. It's another part of their train system. Okay, you'll see the same thing here. 2019, very high numbers. 2020, very high numbers up to March. That's when COVID hit. From March, it kind of becomes very rounding kind of numbers. Same for 2021. We still, even in 2024 and 2025, we're not even halfway to what it was in 2019 and 2020. Okay, so again, substantial challenges. These are all long distance commuters that now, because in Bay Area, because of the technology, there was significantly more working from home. Even now, people are doing hybrid work. There are some policies that are being implemented where people are required to come to work. So this should change in the future. But so again, these data sets would be the starting points for any public transit analysis. You want to do ridership analysis, you're starting at looking at. Okay, now these are very aggregate. Like I'm giving you one number per month or one number per year. This is not what you want to model, but sometimes you would want to go into more deeper numbers because this is I'm giving you one number for the entire system. That's not what you want to use. You want to use more detailed data, but this is just to give you an idea of how the data can be provided. So you'll see different agencies collecting data different. You'll see this is, for example, the monthly data profile here. This is only yearly. This one again is monthly and by different years. So different agencies will compile this information in different things. Now, with smart ticketing systems in place, data collection is easier because as soon as somebody puts in their metro card or so on, you can actually track their origin and destination. If they swipe both sides, in some state transit agencies, you only swipe when you're getting it. You don't swipe when you're getting down because the prices are fixed that way. So in that case, you only get origin data. You don't get where people are getting it. For that, you might have to collect that. So based on the specific system study, there will be specific challenges for the system in collecting data. Okay, so sometimes there is no smart data collection. There's a conductor who punches the holes and gives you tickets. That is very hard to compile, right? Because they go back and report, they provide some numbers, but I'm not sure that's easy to collect for researchers to view, right? And how reliable it is, the mistakes, a lot of mistakes that can happen. And then there's also this challenge of they are not based on the stop, they're based on the reach. So you get in 23 or stop 28, they don't, it's the same price. So there's no way for you to know where they got in or what. So there are some challenges. So this is an example of the ridership. So here is an example of demographic. So what they did is they collect demographic data by conducting survey of transmitters. Okay, so they're going to ask people as you're on the bus or on the metro system, they give you a survey and they ask you where do you live, what is the household size. So again, these are summary. I'm only showing the summary characteristics from their surveys. So for them, these are the important characteristics. For example, average age of respondents is 40, average household income is so on and so forth, and they are able to get some information. So this can be utilized to understand who are the writers. Okay, so they have good proportion of English speakers. You can see there are many languages in San Francisco Bay Area, so there are immigrants from everywhere. Similar data can be collected for every system. You see, look at the income numbers. The last line is something I want. So Muni is used by individuals with an average income of about 90,000. If you look at San Francisco, 53,000. Look at BART, 105. So this kind of shows you the transit system. Okay, so it is used by reasonably high. Beginning in San Francisco, 91,000 is not very high yet. Transit is used by low-income individuals mainly, or lower. BART is individuals high older, majority living in Bay. Okay, so these are the numbers that we see. So this is how demographic data will be available. So, okay, so the data collection and compilation for ridership and demographics are different. When I collect ridership data, I'm not, if I keep asking them what is your age, gender, nobody's going to give you different, right? So that is collected differently than how you're collecting ridership. So you need to figure out to use both efficiently. Okay, so this would be collected in a one-time survey, maybe once a year. If you have a good agency, they do it once or twice in a 5-year window. It's very hard to collect the data, it's expensive. In San Francisco, they're collecting it once or twice every 2 years. So which is a very good data collection. But now, the other thing that we wanted to talk about was travel patterns. So here I'm just showing you an example of travel pattern data. I thought they had a very nice presentation in San Francisco. Let me give this. Data set illustration that they're showing for how San Francisco patterns exist. So here you can select. So these are the main regions. So you see the regions in the San Francisco Bay Area here. Okay. And they are showing you, okay, obviously this is everything. If I select something here, they'll show you travel from that. So, right, so they're looking at Marina Heights here. I selected that. So the wider is the band, the more is the trip. So if you look at this one, so more people are going. So all that there are 285,000 trips going from there. So 4,000, then down. Then so the thinner the band, the fewer is the trip. So it's a very nice way of showing how the demand moves. Again, this is hopefully they got this from a travel demand model and they're aggregating it in this fashion. So you can look at anything you want. So it's a very nice way of data illustration showing where are, so here we are focusing on South Bay. From South Bay, where are the trips going to, which parts of the city they're going to. Okay. So again, this would be a good mechanism. Even if you're just showing your transit data, when you're doing academic papers, it's always good to show the data first. When you're the first section of your data description, again, people are getting tired of looking at tables and average and means and distribution. So again, look for newer ways of presenting the same information because it's more catchy to see something like this than if I just gave you a table of all the ridership, all the flows between A and trade, and it's not easy to show them because once you have this 11 or 12 locations, it becomes a table with 144 cells and nobody's going to look at it. So again, I thought this was very nice. So, and you can also do some of these by purpose and mode of travel. Obviously, once you put walk or bike, the numbers drop substantially. Right? They're not that many. This is transit. So you will see from South Bay, people mainly go to downtown, right? So that's the picture you can see in terms of public transit. So everything else is small. Again, you can also look at Uber and Lyft. You can see a good number to downtown, some numbers to other locations. So this would be the main mode of transportation. Everywhere it's using. Okay, so again, there's also numbers by 2050. So you want to look at change. Okay. It's a very well developed website. You can play around. I have the link if you want to, if you're interested in the slides that is there. So you can look at it. So I thought this was a very nice way of showing some of these relationships. And if you don't select anything, yeah, not here. So this kind of gives you overall trip patterns by trip purpose in the region purpose. Any question? So the last dimension of data that we talked about was the individual data. So this is where we are looking at specific individuals and trying to understand characteristics of. This is also different from the demographic data that was selected. But here we are asking more questions about the individual. We are asking how often do you use the MUI system? So we are asking, so 40% of the people use it 6 to 7 days a week. And then there is a few people who use occasionally, so these are what we call occasionally. So again, we might want to understand who are the people who are using it very often, who are the people who are using it. Again, this would be something that we analyze. And you can ask more information, asking, okay, what changes would get you to use transit mode? So again, this is a very, it's a loaded question because obviously this doesn't necessarily mean that you make those changes and people will use transit mode. It's just what they would like to see. So again, most common comments would be this: they want more frequent service. The current frequency is not enough. They're asking for more reliable, so they don't want the delays that are happening. And again, inner vehicles, slower fares. So again, these are subjective questions which are useful to understand, but they're not going to give you quantitative response. So what I mean by that is, even if you increase frequency, you cannot tell what will be the increase in ridership because of it, right? Because this information is not translatable into quantitative numbers in that fashion. So we need to be careful in using this. A more rigorous approach would be to build stated preference questionnaires where you provide them the new frequency new fare, and then see what is the frequency at which they will adapt this mode and so on. So these are different things that you do. Okay. We did. So the next part, what I want to focus on is we looked at the 4 dimensions. So I don't think the Mentimeter is working well, so I'll stop here. So I wanted to ask some questions on, okay, now given the different dimensions of data we looked at, okay, so what do you think are dimensions that we should study in public transport? What are your thoughts? What would be the ideal ridership way? So let's say you have infinite resources to collect data. So what would you collect and what would you? Louder, louder. Individual ridership, okay?
Because it will help us to overcome the aggregation errors and
Okay.
unit level factor of the.
So how will you collect individual ridership? How many people will you use?
Each population.
So would your idea be to collect data from for each individual or sample? Obviously, you can sample. Would that be your approach, or would it be more beneficial to collect data at the stations or at the? Okay. Okay. So again, depending on what question you are trying to answer, yes, those are valid approaches. You can look at that. Now, if I am a transit agency and I'm trying to figure out how my ridership happens, so I only control what is going on in my system, right? So the easiest way would be I look at my ridership data from the system, right? So and then supplement that with some of the TSDs that are available, other data that you can look at. So you start looking at demand. Now, when you're trying to analyze, you want to look at interactions. What I mean by interactions is how is ridership changing over time, first of all, because populations changes, patterns are changing. Then also, we want to look at how different changes to the system are influencing ridership. Right? So usually, yes, we are running a different line. It's not like it's static. If you change the route sometimes, you change the stop, you change the schedule. So you want to understand the effect of these variables on ridership. Okay? So those are some of the dimensions that we want to look at. Also, for example, in Hyderabad, right? Metro system is relatively new. I wouldn't say it's new anymore, but it's so now what is the impact of that as it stabilizes on bus transit? Because is it increasing bus transit or is it competing? And if there is a coordinated integration efforts made, again, Metro is bus transit, different agency, so it's not necessary that the schedules are coordinated. What I mean by that is ideally what you would want is a bus arriving at a metro stop right before or right after the metro comes. Right? So that way people who are going to get onto the metro can come there and who will leave can also go through. So that way it's a more integrated system. So more people will find that seamless connectivity and use. Now, even to understand that both agencies have to collaborate, but first thing is look at data on what is the impact. So before ridership, what was before metro ridership, what was the bus ridership? What happened after the starting of the metro system? Is it increasing bus ridership or is it reducing? So the impact might not be constant across the entire city, right? There could be locations where they compete, there could be locations where they complement each other, and there could be locations where there is no impact, right? So again, you cannot use a one-size-fits-all approach to all of them. You'll have to do this carefully and look at some of these aspects. So let me go through. One more thing to look at when you're talking about ridership is there are two components to ridership. Right? People get on the bus or on the metro or whatever, and also get down. So there is what's called boarding and alighting. Right? So both are important. So sometimes when people are modeling it, you can add them into one group and model the whole thing. Because it has implications for passenger minds, right? So if you know when a person gets on the bus, and if you know when that person is getting off, you can track the person miles on the transit system. Right? You need both origin and destination to figure it out. If you only know the origin, you know where people are getting on, but you don't know how many miles they're traveling on the public transit system. That is one metric that is important, and especially that if you want to do, we did some work on looking at the person emissions per capita on public transit, right? So a public transit bus, if it goes empty for a long time, it is actually not better than a car. You actually are emitting a lot of pollution when there's nobody. So one way to there are a lot of works assuming average occupancies and then using metrics to generate per capita emissions of public transit. But what we did was we built a micro simulation system. We were simulating boardings and alightings in real. So there's a bus, let's say bus number 100 goes from A to B, which is 20 kilometers long. And along the way, there are 100 stops. Okay? Wherever there is a stop with a person getting on, the bus stops. Otherwise, the bus doesn't stop. Right? So, and it probably runs that 20-kilometer route 6 times in a day or 12 times in a day. So what we did was we predicted ridership at each stop in using micro simulation. So what I mean by that is the bus starts at 6 o'clock in the morning on stop 0. We will run a model, see how many riders will board the bus. That's it. So the simulation comes with 2. So we wait for the 2 people to board. So when the bus is idling, when people are boarding, the more people board, the more idling emissions come into the picture. Okay? So you can do a very high resolution emission, do a simulation of the system like this. So we did that for the entire system of Montreal, Canada, and then we were able to compute because we are simulating it. We know at any instant how many people are on the bus. We have a bus capacity. If the number of people boarding is more than that, so we have a continuous tracker of 3 people are on the bus now. Next stop, 1 person gets down, nobody gets on. Update that number, and we know the distance between the 2 stops. So we can keep track of the person. So there are 6 people on the bus, they went half a mile. So 3 miles. So we can keep track of the total person miles of people. So when we come and we are tracking the speed of the vehicle based on average speeds, and we were able to generate, my colleague emission side, she was able to generate estimates of emissions at a precise resolution based on the roadway segment where they're traveling with the slope and so on. So we were able to generate a very accurate system of person level emissions. So that would show which route. So some routes are very efficient, right? Because they have a lot of ridership, a lot of occupancy that happens, so they're very efficient. But then there will be some routes, so you can actually identify which routes are actually contributing to lower emissions, which routes are contributing to higher emissions. So you can figure out ways to change adding EVs. It might be better to add EVs to the less efficient ones, right? Because these are the systems where there is more pollution, less people are using. But if you have a diesel bus which is always occupied, maybe it's not as bad in terms of the emission. So again, our objective is not to decide on the policy. Our objective is to give mechanisms for policymakers to see where things are. So ridership can be liberated from that perspective. Another thing that we want to analyze is the impact of public transit. Right? So we are looking at providing this public transit system is to increase accessibility. So there are a lot of studies and research efforts looking at how many jobs can people reach using public transit. Can they reach groceries? Again, this is not a problem in majority of India. I think grocery stores are available in close proximity. But in the US, it's a very suburban kind of development. You will have no grocery stores for about 5 to 10 years. So if you don't own a car, it's not easy to walk. So there are what are called transit deserts. Transit deserts because people cannot go to groceries, people cannot go to public health, healthcare, and even other facilities are not available. Okay, so that is something that is very heavily. In the Indian context, it won't be from a desert perspective, but what we're trying to do is improve accessibility. Right? We still want to make sure more people have access to some of. So that is something to look at. And when you are looking at accessibility, another dimension that is important is how are these transit modes accessed. So, for example, in the US, if you have commuter rail, there's a lot of parking in the stations. People drive, park their car, and then take the train. Okay, so now because they're driving, there is an interesting problem that you can look at is people can go to a metro station or a commuter train station which is further away, which is more likely to have parking than a station close to home. If I'm leaving my home at 6 o'clock in the morning, I know I'll get parking. So then I'll go to the closest station. But if I'm leaving at 8 o'clock, maybe the small station's parking is filled. So I actually drive 5 miles and then take transit. So again, there is a question of how do I get to the train station? I can walk or I can take the bus. I can actually drive, and then which station is also a choice that some people will. So some of these analysis is also used. So this is an example of some data that the Chicago transit system provides. Again, just like the chart that I showed you, this is also something we can look at. They provide the ridership information. They provide on-time arrivals of buses if any delays are there. Okay, these are good ways of presenting the information. If you're a transit agency, we look at these as the mechanisms to present, and also I think you can collect. You should be able to collect some data from this to use it to come up with some different metrics for them. And another important thing that we need to look at when you're looking at ridership is you cannot have a one size fits all. I just want to give an example based on what we did in Montreal. So there are 8,000 bus stops in the system for ridership. Okay, but you cannot have a single model for all of them. It's not always helpful to do that because there are some stops which have 8,000 boarding center units. Okay, but there are many stops which have zero. So you need to figure out a good way to characterize those. So that we can call them, cluster them into different groups. So here I am giving an example. So what we did was we did 3 clusters of stops. We looked at stops with low ridership. So this could be a bus stop in the residential neighborhood where maybe 3 or 4 people get on during the day, or up to maximum of 50 people. So what we have is there are stops with ridership less than 50. So these are the low demand stops where they're right next to homes, few people that get on. Then there are what are called medium sized stops where you have ridership anywhere from 50 to 50. This could be stops on collector roads or arterial roads where there is decent demand. And then there are high occupancy stops. So these could be transit centers or locations where multiple bus routes go through them and you have a lot of people use. The largest sample is in the low category. So most of the stops with very little demand, right? So you have about 3,500 in the low category, but in the high category you have fewer stops, but they contribute to the highest amount of ridership. So 18, 13 is the number. Okay? So are you fixing it 11, 15 or 11, 13? Right.
So what may be other way of clustering those stops? Since this is in terms of realized, how about the clustering based on station, placement of the stops? Be it CBD or suburb or various.
Yes.
That can be one.
Yes.
The other can be like their proximity to transit stops. So, proximity to various facilities.
You could do a multivariate clustering also. Right? So here we did this, but you could look at clustering based on land use characteristics, clustering based on location. Like you said, distance. So distance to CBD could be one way, right? So you could use. So if you're looking at clustering for different variables of that nature, I would like doing it by multiple variables, not just right. So you can do clustering based on attributes that you can decide are important. So it could be income of the stop, right? Stop. Yeah, you can do that. So you can use k-means clustering or any of those approaches to create that. And then you can use that. So here our focus was not on that, so we did not do, but that's a valid point. Yes.
Within the four terminal stations, accessibility is almost they were already positioned in such a way they have some similarity
Okay.
for the four stations.
Yes.
And along with that, if the ridership is varying from medium to then only they consider the four stations together to do the
Yes, you can do that. You can do, yeah. So if the total, so here because we have 8,000 stops, we cannot do a station stop specific model. But if you only have, let's say you're saying 4 and 7, you can actually do a model for each station, right? Because there are only 7 of them, right? So you can go more personally. Again, we could still do them. We still do them. You can start adding specific interaction variables for that station. So you can have population, but you can add population times station 1 as an additional column fill. So there is a common effect of population in all 7 stations, but there could be additional effect of population on station 1, station 2, station 3. So you can capture. So that way, even though you are doing a single model, you can provide custom estimates for each station. Okay, so
Here population, we are speaking about the metro.
catchment area variable population, or just as an example, it could be highway or a number of trains. So each terminal might have different number of trains coming at different points, things like that. And then also what is around that station, right? Within half a mile or 1 mile or 1 kilometer. Each station will have different characteristics.
we can't combine this then it can be individual and
No, the variable will be the same for all 7, right? The name. So let's say I'm capturing, let's call it M1, number of jobs within 1 kilometer distance from the station, right? So for station 1, the number of jobs would be 3,000. So, but it still is, so my independent variable is M1. So I can come. Right? Another challenge in this is you have only say, but you will have multiple days of data. The challenge here is that you have repetitions for the same station.
for example, ordinary considering the for example the four terminal stations there are only two variables for the station by considering and the ridership. And ridership is going to taken certain limit if it is in this direction the station will be handled. And so we have clustered the station. And for that particular station, if we are considering about 10 variables, then can we plug these four stations together?
Now you have to be careful. You have to be careful with combine. You can combine them. So there is an approach called pooled model development, where when you are developing the pooled model, I can develop specific to any observation, but do it jointly. There's a mechanism to do that. So you need to create what about so for every variable, let's say you have 3 variables. Just as an example, right? So let's say population, income, and ridership are the 3 variables. For each of these 3 columns of data, I can create multiple copies of it by multiplying with a dummy variable. So what I do is population times station 1. What that means is if it is for station 1, the population is multiplied with 1, otherwise I multiply with 0. So if you have a column of data, the first column there is population only, in the second column I have population station 1. So that population variable is seen only for station and 0 elsewhere. Similarly, population station 2 will be 0 for station 1, population for station 2, 0 for everything else. So you can create, you have 10 stations, you can create 10 columns, 10 sets of columns like that. And you introduce one base, which is the variable, and you can introduce interactions. So that way, in a single model, you can actually capture impact. The reason this is used, this is efficient, is because population might not be different for 6 stations. The effect of population. So if you do separate models, you get 6 coefficients. But if you do one base model and 5 interactions, and all 5 interactions are insignificant, you will recognize that population. So that analysis is easier. Separate models will get share of population is, let's say, 3 in one, 3.5 in the other. You will say, you think they're different, but in reality, statistically, they're not different. Okay, so that's very good. We can talk about, if you have data, we can actually talk about how to do it. So other dimension that we can focus on is also system operation. So for example, there is focus on understanding travel times per route. So which are the routes? If you're a, this is a supply side problem, right? There is a demand side problem which is ridership. If you look at the supply side, you're making sure the infrastructure is enough or not. You want travel time reliability to be an important aspect. How much on-time arrivals are happening? What are the delays and so on? And then you also want to make sure there is analysis being conducted on understanding how much time are people waiting for the bus, right? And then much is the walk time in the people have. So these are things that something that might be looked at. Customer satisfaction, again, the perception survey is conducted to understand whether it is serving the needs of the people. So these are all elements that you can analyze. The last component I identified is societal impact, where you can look at how using it reduces private vehicle usage, hopefully reduces emissions and so on. The role of public transit goes beyond just transporting people, right? So there is, if you look at, it changes the communities, improving connections between communities. There is a tangible value of that. There is also positive improvements to property values in look at transport. All of these are examples of locations where the property before the metro station or the station into existence, that region was not as prosperous. But once it comes in, new retail, new facilities, new schools to existence, and that change the land. So those are things that are important to measure. So we talked about the dimensions. I want to talk about how to analyze, right? So I want to model leadership. Usually it is modeled as boardings or lightings. So it could be stop level, it could be region level, and so on. So the variable is right? So if the ridership numbers can be large in some cases. So if you have those large numbers, if you only see 0 through 5, maybe you don't want to do linear regression, you want to do ordinal models. But if you see numbers going from 0 to 150 to 100 and so on, you might use linear regression or count. We'll talk about. If you're modeling travel time, again, it's a continuous variable that requires linear regression. If you're looking at impact of transit and you're modeling property values, these are continuous numbers. Again, which you can use what is called a hedonic regression model. But if you're looking at mode choice, station choice, and route choice, there we get into categorical way. Okay? In those cases, we will use discrete choice models such as multinomial logit, nested logit, and so on. If you're looking at customer satisfaction, this is something that is done routinely at different transit agencies. Let's say they go from customers are very happy, very good, good, fair, poor, very poor. So this is an example of an ordinary. From very positive to very negative. So it is more appropriate to use order response models. Yeah, okay. So basically what I'm doing with the we need to understand how linear regression models work, how categorical models work, how order response models work for understanding different facets of data. So in the next coming sessions, we'll talk about those models, and also I want to talk about some supplementary data. So I'll pause here, but we'll talk about the supplementary data also, and then move on. Okay, thank you.